this is our last of our speaker is Dr. Kristina Oganesyan. Sorry, my pronunciation is too bad. So let's welcome her. Thank you.
Thank you very much. And I would like to thank the organizers for the opportunity to be here, to give this talk. So this place is very special for me. I was here 5 years ago at the workshop, which was the ancestor of this one. And that was my first big conference. I was a master's student at that time. And I would say that that week at Isaac Newton Institute was really crucial for me to choose the academic way. So I'm really happy to be here again. And let us start with the following result by Philip Jamming that says that if we have a square integrable function in Rd and we want to compute the integral of its Fourier transform, the square of its Fourier transform, on some measurable set, then this integral will lose to the integral, this is the corresponding integral for its decreasing rearrangement on this ball centered at the origin, having the same measure as your initial set. This constant here depends only on the dimension. So, and this is just one slide we have multidimensional. So from now on, we will deal with the real line, and our focus will be on the cases when we can remove this constant. Just put one.
Sorry, what is F star? What is star?
Here.
What is it?
So it's the symmetric decreasing rearrangement. From now on, we will. Yes. We'll deal just with a one-dimensional case, and I will fix this normalization. For me, sinc x will be sine pi x over pi x, and I will choose this normalization for Fourier transform. So a result by Donoghue and Stark says that, okay, if your function is supported on the set of measure t, it's square integrable, then if I want to measure this L2 norm of the Fourier transform, taken not over the whole line, but over this symmetric interval, then it's better to rearrange your function. Then it will give you the bigger integral. If the following holds, so the product of the length of your interval and the measure of your set is bounded by this constant T naught here. And okay, a couple of important observations here. First, that actually we don't have two parameters, T and W. So by means of dilation, we can fix one of them and work with just with the other one. So the important parameter is the product, really. And another observation is that T naught is sharp. So if we allow the function to have Wt greater than this value here, then we can find a counterexample to this inequality. How can we prove this? So first of all, we write down the expression for this integral. We obtain this expression here, and then we use the Riesz inequality that says that we can put rearrangements on F and on sinc here. But the important thing that under the conditions of Donoghue-Stark theorem, we have that the argument of sinc here is supported on is in this interval minus T naught, and what is T naught? So let me draw the graph of sinc. It goes like this, and T naught is exactly the point when we first attain the maximum. So it's 1, it's 2, and so on. And this is the maximum of over all x greater than 1. And the point when we first attain this maximum is, by the definition, T naught. So this means that the rearrangement of sinc here is just sinc itself. So we can remove the star and we recover this L2 norm of the rearrangement, which is greater. Okay, as I said, we cannot do anything better in this case. But what if we consider only the case when f is characteristic function of some set? So we write the same expression and we get this integral of sinc. And there are two things that we can say about the extremizers. So if we look at the set that extremize this, that maximize this quantity here, then it should be the superlevel set of the following function. This function actually depends on your set. So fa will be the integral over a sinc x minus t dt. This is the first point, and the second point that it actually should be a finite union of intervals. So if I draw this finite union of intervals, I draw the fa for this, fa of x, for this set, it should be something like this. Something like this, and at the end points of the intervals, the values should be the same. So that's what we can say at first glance about these extremizers. Okay, and then we can prove that for our particular case of characteristic functions, we can enlarge the range provided by Donoghue and Stark, which we saw is sharp. So we can put here at least these 4/3. And how do we do this? The idea is to, okay, let's consider these extremizers, which by our assumption will be not just a single interval, but several intervals. And then we can see that the value of fa at these points should be large. At all these points should be large. In particular, if you integrate this sinc x minus the first point plus sinc x minus the very last point, you have to get something big. And in the case when your measure is quite small, it's 4/3, these holes you have here, they really play against you. So that's basically the idea here. And okay, let us analyze a little bit this difference. So I have this L2 norm for the interval, and I have L2 norm for the union of intervals of the same total length. If I write everything down, I get this expression. So let me write this. So I have this here, and let me write not the integral of c, but some arbitrary function phi here. So it would be this sum plus the last term, which is phi of this sum. Okay, and let me call it t phi of xj. Okay, so we can see in particular, if we play a little bit with this expression here, we can see that if we put phi equals x, then tx will be always 0. Okay, you can rewrite it as these weighted L2 norms or these non-harmonic polynomials generated by the endpoints of your intervals. And using this, and actually using this observation here, you can multiply your xj's by the same factor that goes to infinity, and then you obtain this equality. So whatever your intervals are, the important thing for this norm is just the sum of the length. Okay, and using this, the first thing that we can derive is this bound. So whenever we have this non-harmonic polynomial, we can bound it, this L2 norm, by this value here, which, well, we can note that the straightforward estimate would give you quadratic order in this sum and not linear, as you can see here. Okay, now we're ready to formulate the conjecture. So actually what we believe is that no matter the length of the interval, no matter the measure of your set, they always should hold this inequality. And okay, using this expression here, we can rewrite this conjecture in terms of the L2 norms of non-harmonic polynomials in this way. So if you can prove the second conjecture, we are good because of that expression we obtained. So it's the same. Okay, why should it be true? What are intuitions for this to be true? Let me present one of these intuitions. So let me consider just the case of two intervals. If you write everything down, you obtain that expression. And well, the first question may be, why is it symmetric in A, B, and C? Let's draw a picture here. So I have an interval A, an interval, say, the whole will be B, the interval C. And let me, for a moment, introduce this product. So for two sets, X and Y, I will call this by a product, which will be just the integral of sinc over these two sets. Okay, and what I'm supposed to maximize is the product of A plus C, A plus C, right? So I can write everything down. I have AA plus CC plus twice AC. So AA and CC, they do not depend on this whole. So if I move A and C, these terms here are the same, and I have to care about this last term, right? Okay, and if A is greater than B, then moving these two intervals together is the same as to cut an interval of length B here and to put it into the whole, right? So that gives the understanding why having an interval of length A whole of length B, an interval of length C is the same as having an interval of length B, a whole of length A, and an interval of length T. So the symmetry here is not surprising. And okay, if you're collecting all the terms together, you get this expression here. And look, sinc is periodic with period 1. It's non-negative. And if A, B, and C are integers, positive integers, then this expression here is positive. And you can do the same for the case of n intervals. So the first intuition is that if you're integrating sinc squared near the origin, it's better, because you have this factor 1 over t squared. And that's the intuition. Okay, now what we have for two intervals, the easiest case we can imagine is two intervals, and in this case it's really better to bring the intervals together in order to increase this L2 norm here. One very easy corollary of this is that, okay, if we have three intervals, just three intervals, and for some reason we're very happy and this whole here is the same as the length of the interval here, then it's better to put this interval into the whole. Why? Because the product of these two intervals will increase, the products of these two intervals will increase by the theorem, and we are done. So a very simple example, just to fill in with the flavor. Okay, another useful observation here, that even if we can do something better than an interval, it's still bounded by some constant. Why? Because actually the interval approximates very well the whole integral of your Fourier transform. So you can see that this integral here cannot exceed the integral over the whole line, which is the L2 norm, which is exactly the measure of your set. So and this is bounded by a constant. So interval is very good already. So the best you can do is to overcome this integral by some constant which does not depend on the measure of your set, not on the points you choose. But there is another inequality. So if you have your set being a finite union of intervals, then they are kind of approximating well the situation of one interval. What do I mean? I mean that this bound here doesn't depend on the points once again. It only depends on the number of intervals. So this bound goes worse when you have too many intervals, but the important thing that it doesn't depend on the points and on the measure of your set. And using this argument, actually, you can prove another bound for the non-harmonic polynomials. So the previous bound we saw was, let me write it here. It was the sum. So it was this sum here, which did not depend on the number of intervals. It just depended on the length of the set. And now it depends only on the number of intervals, which is optimal in the sense of up to a constant. It's optimal because if you choose alphas with big gaps between them, then you have the lower bound of order n by the Inium inequality. So I would like to stop here. Thank you very much.